next door for this distinguished paper talk. I hope I won't disappoint you. So today I'm going to talk about our work on RustBelt to meet relaxed memory, which is the adaptation of the RustBelt verification effort into a more realistic relaxed memory model. And you're probably wondering what RustBelt is, right? So RustBelt is the first work on the formal foundation of the Rust programming language. These works were published 2 years ago, also at POPL. It reported a huge verification effort, and honor proofs were done in Cork. However, why this is a very big step forward for the formal foundation of the Rust programming language, it is only the first step. In particular, in that work, the authors assume for the semantics of their language a simple concurrency model, which is the sequential consistency model, which does not really reflect the actual concurrency model that Rust uses, which is C11. And in this work, we make another step forward, that is to port this huge verification effort into a more realistic concurrency model that is much closer to the actual Rust memory model. So there are a lot of details in this work, and in the interest of time in this talk, I can only give you a high-level overview of the adaptation of what we need to do in order to port this to relaxed memory. And then in the second part of the talk, I will give you a very quick glimpse into one of our main technical challenges, which is about resource reclamation in relaxed memory. But first, let me give you a review of the Rust programming language and RustBelt. So Rust is a system programming language developed at Mozilla. It's a system programming language in the sense that it provides low-level control over memory resources, like what you can do in C and C++. However, it does still provide high-level guarantees like type safety, memory safety, and thread safety. And the way Rust achieves these safety properties is through a substructural type system, where you can find types with ownerships, borrows, and lifetimes. The details of these concepts are not important for this talk. The key point here is that the observation that historically the unrestricted mixing of mutation and aliasing to the same object at the same time has been a reliable source of memory errors, concurrency errors, and so Rust prevents these errors by simply disallowing mixing mutation and aliasing in its type system. In particular, you either can mutate the object, but there should be no aliases to it, or you can have multiple aliases to the object, but then the object should not be mutable. And most of the time, you would write code that fits into this restriction, which form the so-called safe fragment of the language. But however, when you want to implement more, say, intricate algorithms or data structures, like memory management mechanism or concurrency synchronization mechanism, you would need to, this safe fragment would be too restrictive, and you would need to use unsafe code. And in these unsafe code blocks, Rust allow you to use more potentially dangerous operations. For example, you can do raw pointer manipulation like in C, in C++, or you can call foreign functions from other languages. And the type system will not check your unsafe code. It is your responsibility to make sure that these potentially dangerous operations are actually safe. And so the situation now is that with the Rust programming language, you can write programs that mix safe code, which is checked by the type system automatically, and unsafe code, which is checked only manually by the developers. It's now not obvious how, when you write such a program that mix safe and unsafe code, your program is still safe, meaning that when you execute it, there will be no errors. And so this is the exactly the question that the RustBelt project studies. It aims to formalize and validate Rust safety claims in the presence of mixing safe and unsafe Rust code. And the way that RustBelt approached this problem is through the so-called semantic approach. And in this approach, there are two main tasks. One concerns the safe fragment of the language, and the other one naturally concerns the unsafe fragment. So for the safe fragment, we need to prove once and for all the soundness theorem of the syntactic type system. We say that any code that has been checked by the type system, any syntactically well-typed code, is actually behaviorally safe, meaning that it will execute without error. And then for every new libraries that you write that internally use unsafe code, you have to manually do verification to make sure that these libraries are actually also behaviorally safe. And the key important point is that behavioral safety is formalized in a way such that it is composable, so that when you mix your safe code with your verified unsafe code, your whole program is still behaviorally safe, which means that it will execute without errors. So that is the high-level explanation of the RustBelt approach. So in order to explain the actual adaptation of how we do this to move this to relaxed memory, let me give you a more closer view of the actual proof structure of the original RustBelt work. So in that work, the author started out by first defining the lambda Rust language, which is a lambda calculus model of the Rust language. And it's defined with a type system that models Rust type system, which has ownerships and borrows and lifetimes. And the author then instantiated lambda Rust in this Iris framework, which is a framework for building higher order concurrent separation logics, which are very important in order to be able to have some modular proof structure such that we can deal with the complexity of the language with some reasonable verification effort. And so the authors used the framework to derive a concurrent separation logic for this lambda Rust language. They then built another more abstract separation logic on top of this logic called the lifetime logics, which allow you to reason not just about ownership, but also about lifetimes and borrows, which are the key components of the Rust type system. And then they use that lifetime logic to prove the soundness theorem of the syntactic type system. Now, in the second text concerning the libraries that use unsafe code, the authors demonstrate that they can verify some of the most common libraries, standard Rust standard libraries that use unsafe code. In particular, they verify a few sequential libraries like reference counting self, ref self, and some concurrent libraries like like mutex or reader lock or atomic reference counting. So this is the high-level proof structure of the original work, right? And in this work, what we want to do is we want to replace this block in the bottom right here with a more realistic relaxed memory model. So what we did actually, we first, I don't know, this doesn't work. Yes. So we first define our relaxed memory model, which we call ORC11 or ORC11. This is a operational semantics, operationalized version of the repair C11 semantics, which is the fixed version of C11. And in this semantics, we have non-atomic accessory, we have relaxed accessory and fences. We also have release of Y, that means it's very close to the actual Rust memory model. We combine this ORC11 semantics with the lambda Rust language to get our actual language, and then instantiate it in Iris again to build a new concurrent separation logic for relaxed memory. This time, we call it IRC11. And we use this IRC11 to reprove the lifetime logic with respect to our new semantic. Fortunately, we managed to do so without changing much of the interface of the lifetime logic, so that we can basically reuse the soundness proof of the syntactic type system, because this proof mostly only depends on the lifetime logic. And then in the second task, we have to re-verify our libraries that use unsafe code with respect to the new semantics and the new logic. Fortunately, the new semantics only changes in the concurrency aspect, so that we don't actually have to redo the verification of sequential libraries. And then in the re-verification of the concurrent libraries, we have to deal with the actual now relaxed memory operation that these libraries can actually use for our new semantics. And in the process of doing so, we actually found a bug, a data race in the atomic reference counting library, very subtle bug. And this bug has been reported and has been fixed in the Rust code base. So that is the high-level overview of the adaptation of the RustBelt verification effort into relaxed memory. We call this RustBelt relaxed, obviously. And there are a lot of contributions, technical contributions in this work. We have a new operation semantics for relaxed memory, called ORC11. We have a new logic for this semantics, which have a lot of features, including resource reclamation, which I will come back in the second part of the talk. We have a new verification of very subtle concurrent libraries that Rust built. And all of this actually is more applicable beyond the Rust programming language. It can be applied to any languages that rely on the RC11 memory model or any models that is stronger than that. We also have a new soundness proof of the lifetime logic, which is really specific to RustBelt. But more importantly, we managed to reuse the original RustBelt work, 2/3 of the original RustBelt work. We particularly, we reused 10,000 lines of code out of the original 15,000 lines. And you can see that we actually go up to 36,000 lines of code. And the reuse is mostly in the type system, in the type soundness proof, in the sequential library verifications. And we managed to do this thanks to the modular proof structure that we get from using a concurrent separation logic framework like Iris. And so there are a lot of, like I said, there are a lot of details. If you are interested, please read the paper or come talk to me. In the remaining time, I will give you a very quick glimpse into one of our main technical challenges, which is about resource reclamation in relaxed memory. So what do I mean by resource reclamation? The traditional form of resource reclamation is simply that once you are done using your resources, whether this is memory or file resources or whatever kind of resources, you simply call the destructor to return the resource. And we naturally have to deal with this in verifying libraries that use unsafe code. But in the context of the Rust programming language, there's another form of resource reclamation. In particular, you can have resources in Rust that can be borrowed by another party for some lifetime. And when the lifetime ends, which you don't know when, this resource must be returned to the original owner. So now we have this form of resource reclamation that is tied to lifetimes. And we have to deal with this in the type system, in particular improving the type soundness of the type soundness theorem, and more specifically improving the soundness of the lifetime logic. And unfortunately, in relaxed memory logic, we do not have adequate, in previous logic, we do not have adequate support to deal with these form of reclamation that Rust actually needs. And so this is one of our main challenges. And in particular, in dealing with reclamation, we have to maintain this property that I believe most of you would know, which is just say that no use after free. Meaning that, once you reclaim the resources, nobody should be able to use those resources. And the problem is that it's more subtle to maintain this property in relaxed memory. In order to understand why, let me just give you a very quick example of this no use after free principle in sequential consistency, and then I will explain why it's more subtle in relaxed memory. So in this example, we have two threads running concurrently, and they are also concurrently accessing the location X. And at the end, thread 2 will be responsible for reclaiming X by calling free X. And the two threads coordinate by using a flag Y. So thread 1 simply set Y to 1, and thread 2 simply wait for that right by keep reading Y. And once that is established, thread 1 has sent a signal to thread 2, and thread 2 simply then can free X. And this maintains the no use after free principle, because we know for sure that the free of X is executed after, this should say after, sorry, or something. Maybe I don't have the, okay. It's frozen? Yeah. Okay, the read, because the read of 1 to Y is executed before the free of X, and we also know that all of these concurrent accesses to X is executed before the read of Y, so we all know that all the uses of X is executed before the free of X, right? And that's no use after free. Very simple in sequential consistency. However, in relaxed memory, there's a problem. In particular, in relaxed memory, the execution order is no longer coincide with synchronization. In particular, even if you know that the read of 1 to Y from Y here by the second thread is executed after the write of 1 to Y by the first thread, if you happen to use a so weak access mode, in this case I'm using relax, then there will be no guaranteed synchronization between the two threads. And in that case, it might be possible that the free of X by the second thread is racing with the accesses to X by the first thread. Formally, this synchronization is defined by the happens before relation. And in this case, if we are using relaxed accesses to y, then we are not guarantee a happens before relation between the accesses to x by the first thread and the free of x by the second thread. And by definition, that is the data race. So in relaxed memory, we can no longer just care about execution order. In fact, we have to forget about it and focus on happens before. And our principle is no longer just no use after free, but it's actually no use not happens before free, which nobody can understand. So let's just remove the double negation. And the principles say that, well, you should have use happens before free. We simply say that concurrent accesses to the share resources. So remember that I'm generalizing to resources, right? Concurrent accesses to resources must happen before their reclamation. And our goal now is to build relaxed memory logic that allows us to do reclamation and still maintain this use happens before free property. And so we ask ourselves, well, how was reclamation done in sequential consistency, and can we port that to relaxed memory such that it still maintains use happens before free? And so in the original RustBelt work, in order to do reclamation in sequential consistency, there's a mechanism called cancelable invariance, which I'm showing you the rules here, but if you don't know concurrent separation logic, you don't need to read them. I'll try to explain them with some high-level points. So the first thing is that in this concurrent separation logic, in order to be able to have share accesses to resources, you need to put the resources inside invariants. Right? And if you want to reclaim those resources, you want those invariants to be cancelable. And so cancelable invariant has two main mechanisms. One is accessing the invariant, and the other one is canceling the invariant. And both mechanisms concern the new assertion called the invariant token, showing up here as tau q or tau 1. And the access rules say that, well, if you have only a fraction of this token, you can access the invariant content. This is important because then you can split the token into multiple fractions, and then multiple parties can concurrently access the invariants. And once the multiple parties have finished accessing the invariant, you can recollect all of these fractions into the full token, tau 1, and only then can you use the full token to cancel the invariant and reclaim the resources, and basically ending the concurrent sharing access mode. So this is a very simple mechanism. Oh, almost done. But our question now is that, can we also have this in relaxed memory and still, in order to have reclamation and still maintain the use happens before free property? The problem has been that specifically in the modeling of this invariant tokens. So previously, in previous logic, the invariant token has been modeled with ghost state. But in relaxed memory, a ghost state can be transferred without synchronization, and this is not good for our model, because if we model our token as ghost state, we'll be able to reclaim the full tokens without full synchronization, and that is a direct violation of the use happens before free property. And so we cannot simply just use ghost state to model invariant tokens. And the solution is to introduce a new kind of ghost state, which we call synchronized ghost state. Meaning that the ghost state can only be transferred across thread with synchronization, and this is a suitable model to port cancelable invariants to relaxed memory so that we can have reclamation and still maintain the no use after free, the use happens before free principle. And I would love to show you more rules, but unfortunately I'm already out of time, so I will stop talking and show you the high-level overview. Thank you.
Time for one quick question.
Thanks. So if I read slide 12 rightly, so ORC11 does not have any SC accesses. So you've gone from a world where everything is an SC access to nothing is an SC access, which is, I guess, kind of striking. Can you comment on that?
So the thing is that, well, the exact behaviors of accesses are not clear. We have existences, but also the thing is that for the libraries that we verify, they don't actually use any SC accesses or SC fences at all. Yes.
Yeah. Oh. Okay, there's an anonymous question. from your experience in proving the unsafe libraries, is it doable by any Rust user, or can we automate this?
Well, my experience with these libraries is that these libraries are extremely difficult, even for manual proof, to understand what is the actual reasoning why these are safe, and that's why there's a bug in this atomic reference counting. So right now, even doing it manually is already hard enough. I don't know about possible automated verification.
Okay, thank you. Let's thank Hoang again.